Today we're talking about nonmetal reactivity and electron affinity and their trends on the periodic table. So the day before we talked about metal reactivity, and we said that metals react by losing electrons. Today we're talking about nonmetals, and nonmetals are on the right side of the periodic table here. They're to the right of the staircase. And typically when you give a nonmetal atom a charge, usually that charge is negative, which means that the nonmetals gain electrons when they become charged or when they bond. And so nonmetals typically gain electrons, which is the opposite of metals, losing electrons. Now the reason why nonmetals typically gain electrons is because they have a high number of valence electrons typically. And so, for example, if you look at the halogen family, they have 7 valence electrons, the oxygen family have 6, the nitrogen family have 5, and so it is much easier, or it requires less energy to gain a few electrons than it is to lose a whole bunch. So nonmetals typically react by gaining electrons. So they are the opposite of metals. So again, nonmetals react by gaining electrons. Now, remember that the atom has a nucleus where there is a positive charge because of the protons, and then the electrons are outside in the electron cloud, and there is an attraction between the electrons and the protons because of the positive and the negative. I'm actually going to draw 2 of them here. Okay, so again, there's an attraction between the positive and the negative. Remember also, the day before when we were talking about metals and ionization energy, we said an analogy. So we kind of talked about electrons, kind of like chocolate, if you will, and energy being like money. And so we said we kind of exchanged the chocolate for money. So we said, let's say you have an atom, and it wants to, or it has electrons here, and it's electron cloud, when we're going to lose those electrons. And so we said that that analogy would be like if you were the atom, and you had chocolates, and we were trying to take away a piece of chocolate from you. Because you like the chocolate because of that positive and negative attraction, in order to remove the electron away from you, or to remove the chocolate away from you, we have to pay you money. And so we said if you remove the electron away from the atom, you have to give it energy. There's an exchange. I take your chocolate, I give you money instead. So I take the electron away, I give the energy instead to the atom. Now that's the case with metals. Now let's look at nonmetals. Nonmetals tend to gain electrons. And so if you are the atom and you had some chocolate, but then you wanted an extra piece of chocolate, so you're going to gain that extra chocolate. In order for you to get extra chocolate, you now have to pay somebody money. And so if the electron is actually being gained by the atom will give away energy. So let's repeat that again. If you were the atom and you were losing an electron, we have to give you energy. So the atom absorbs energy, or energy is required to remove that electron away from it. However, if you were the atom and you were gaining extra electrons because you like those electrons, if you gain an extra electrons, then you have to pay energy or release energy. The more you like that electron and you want to gain it, the more energy you're willing to release. That energy released is called electron affinity. And so electron affinity is the energy released when an electron is gained. Since this is energy, it's going to be measured in joules or kilojoules. Okay. Now, another word for affinity is liking. So this is the same thing as electron liking. If I have high affinity for chocolate, for example, that means I like chocolate. So if you have high electron affinity, that means you like the electron. The more the atom likes the electron or has high affinity for the electron, the more energy it's willing to release in order to gain that electron. So the higher the electron affinity, that means the higher the electron liking, the more energy released to gain the electron. Okay. Now we did a couple of demos in class. Obviously I can't do these here. We looked at the halogen family and we found out that reactivity for halogens actually decreases as you go down. And we kind of talked about it, but basically fluorine ends up being the most reactive nonmetal. Now I don't know if you remember from the day before we were talking about metals, francium is actually the most reactive metal. So this is the most reactive metal. This one is the most reactive nonmetal. Now notice that they are like on opposite sides of the periodic table. They're the opposite corners of the periodic table. That should make sense because their reactivity is different. The metals react by losing electrons. The nonmetals react by gaining electrons. So basically we're saying that francium is the easiest to lose an electron. Fluorine is the easiest to gain an electron. So imagine if there was a reaction between francium and fluorine. That would be probably one of the biggest reactions there. So if you were not here for the demos, basically what I'd like to do is kind of go through the reasoning. Remember, all these trends have to do with where the electrons are in the atom and the attraction between the electrons and the nucleus. So let's try to reason our way through the trends. So let's come up with the reasons first, and then see if we can come up with the trend from the reason. So I'm going to start with going down the periodic table. So first thing you want to always mention is where the electrons are added. So down the periodic table, electrons are added to additional energy levels. Okay? Since they're added to new energy levels or additional energy levels and they're farther and farther away from the nucleus, second thing you usually want to comment on or mention is Zeph, which is the attraction between the protons and the nucleus. So since the electrons are being added to new energy levels, that attraction decreases. So I'm going to write that down. Zeph, which is the attraction of the nucleus to the electrons, decreases. There's not as much attraction. Okay? Now, let's talk about nonmetal reactivity. Remember we said nonmetals react by gaining electrons. So let's think about this. If the protons are not pulling in the electrons as much, there's not as much attraction. Would it be easier or harder for the atom to attract an extra electron or to gain an extra electron? Since there's not as much attraction, it is harder for the proton to pull in an extra electron. And so it's harder to gain an electron. And since it's harder to gain an electron, that means it's harder for the nonmetal to react, because nonmetals react by gaining electrons. And so that means that the reactivity would decrease. So see how we came up with the trend from the reason? Now let's think about electron affinity. I actually prefer to think about electron affinity as electron liking. Since the Zeph, or the attraction, decreases, there's not as much attraction, that means there's less electron liking, so that also decreases. Let's also think about it in terms of energy. So electron affinity is how much energy released when the atom gains an electron. Since there's not as much attraction between the protons and the electrons, that means that the atom is less likely to give energy in order to gain the electron. So less energy released to gain the electron. It's kind of like you don't like chocolate as much, so you're less likely to pay money for it. And so again, the trend would be that it decreases. Now let's look at across a period. So again, for across a period, we are going to start by talking about where the electrons are being added. So electrons are added to the same energy level. Now, because the electrons are added to the same energy level, that means Zeph, which is the attraction between nucleus and electrons, increases. There's a lot more attraction now between the protons and the electrons. So let's think again about nonmetal reactivity. Nonmetals react by gaining electrons. If there's a lot of attraction between the nucleus and the electrons, now the nucleus has a strong pull on the electrons, so it's easier to grab in an extra electron or attract it in. And so it is easier to gain an electron, which means it's easier for nonmetals to react. Reactivity of nonmetals increases. Now let's think about electron affinity. Remember, electron affinity means electron liking. If there's a strong attraction between the nucleus and the electrons, that means the atom likes the electrons a lot, and so that increases. But let's think about it also in terms of energy. Electron affinity, again, is the energy released when you gain an electron. If there's a very strong attraction between the atom or the nucleus and the electrons, that means that the atom is willing to give away lots of energy in order to gain the electron. If you love chocolate so much, you're willing to pay a lot of money in order to gain a piece of chocolate. And so more energy released to gain an electron. Okay, let's take a look at graph that you have. I'm sorry that students can very well. There's a couple of things here that are kind of interesting that you wouldn't expect. So let's take a look at the graph here. Now you would notice that a lot of the numbers there are negative. Remember, we're plotting energy. Is there such thing as negative energy? Well, there's not negative energy, but basically when it comes to energy, energy is either released or absorbed. And so in order to know whether it's released or absorbed, we give it a sign. And so if it's positive, if the value for energy is positive, that means that energy is being absorbed. If the value is negative, that means energy is being released. Remember that electron affinity is the energy released when an electron is gained. So typically, when the atom gains an electron, it releases energy. And so you'll see that most of your values are negative. There are only a few values that are positive here, and so these are exceptions. Most of the time, it is favorable to gain an electron, and so the atom actually releases energy, like we talked about. what I'd like you to look at is also the values. Now, the high negative values. We said that negative means that energy is released. So high negative values means that a lot of energy is released. So down here, these are the elements that have the most energy released. Up there is the least energy released. Okay? Remember we said the most energy released means the high electron affinity is. So electron affinity is the energy released, and so the higher the electron affinity, the higher the energy released. So these on the bottom actually have the highest electron affinity. And these up here have the lowest electron affinity. So when you're filling out your table on the back, that summary table in the back of your packet, it asks you what are the peaks and what are the valleys. So these have the highest electron affinity, so these are actually our peaks. And these have the lowest electron affinity, so these are actually our valleys in terms of electron affinity. Lowest electron affinity and highest electron affinity. So let's look at what groups these are. If you look right here, this is atomic number 9, so this is fluorine. This one looks like chlorine, and this one looks like bromine there. And so looks like the halogens have the highest electron affinity. Now, does that make sense? Yes, it should, because the halogens want the electrons the most. Remember, they have 7 valence electrons. They need only 1 to become stable, and so these have the highest electron affinity. So if you look at a periodic table, fluorine is the most electronegative. Has the highest electron affinity. Now, we would expect that those top values would belong to the alkali metals, because according to the trend we've just looked at, electron affinity should increase as you go across a table. Turns out, though, that's not true. This right here is beryllium. This is atomic number 12, so that's magnesium. This one's 20, so that's calcium. Look at that. These are group 2 metals. Now let's think about that. Why would group 2 be the least willing to gain an electron? Why would it be the worst for them to gain an electron? Now, if I ask you that on the test, that would be an extra credit question. But basically, the reason is because if you look at, see, group 1 on the periodic table, I should have had a periodic table down here. So the periodic table kind of looks like this. Okay. So these are your transition metals here. This is group 1, group 2. If you look at group 1, they end with S1. Group 2 ends with S2 in their electron configurations. This would be S2P1, S2P2, and so on. So if you have something in the first group, S1, if it gains an electron, it becomes an S2. Now, group 1 would like to lose the electrons, but if it gains an extra electron, its S sublevel will just be filled. You know, that's all right. However, if you look at the S2, if they gain an extra electron, they go from S2 to S2P1. They put in the extra electron in a whole new sublevel, and that makes it very, very unstable or higher in energy compared to the S2. They already had a full S, and now you're adding an extra electron into the P, and so that is very unfavorable. Again, that would be an extra credit question. If I ask you about that, you'd show me that group 1 would go from S1 to S2. You'd maybe give me an example and show me the electron configuration. So this is not as bad as this one right here. Now the last thing that I wanted to point out is if you look at the values that you graphed, we didn't really talk about the noble gases at all. They're not, the values are not on the table that you graphed here. And so the reason why the noble gases are not included is because the noble gases right here are not very reactive. And so they don't want to gain an electron, and so they have no electron affinity. They don't like the electrons. You can't gain an electron, so we can't measure how much energy is released when they gain an electron. And so the group that's absent from here are, again, your noble gases. So you have to watch out when you're ranking different elements on the periodic table in terms of electron affinity, because the electron affinity increases as you go across. That's a trend, but it stops at the halogens. So, for example, let's say that this is, for example, neon, and this is fluorine, and this is oxygen, this is nitrogen, and carbon. So let's say that I tell you, hey, please rank these elements in order of increasing electron affinity. The correct ranking would be neon, then carbon, then nitrogen, then oxygen, then fluorine. So yes, the trend increases as you go across, but it stops right here at the halogens because the noble gases have no electron affinity. So they actually have the lowest electron affinity of all of them. So neon has the lowest, then followed by carbon, nitrogen, oxygen, then fluorine. Okay? Hopefully this helps, guys. Let me know if you have any questions.